Hey, here's what we're going to be talking about today. Prime numbers. Is one prime or composite? Now look, if I do a good job with this video, some of it you're not going to like. Some of it's going to make you a little sad because you're going to be confused. However, if I do a good job, I will resolve that confusion and you will become happy. Well, not dead. That's crossed out. Anyway, if I do a bad job, you are never going to be confused. You're going to be happy and just wonderful the whole time. You're going to think it's concise and clear and easy to understand, but the truth of it is you won't have learned anything. So bear with me. If you get confused, feel free to always pause the video and think about it for a minute, and I will resolve any points of confusion before we finish. So let's get started. The number 1, is it prime or is it composite? Which camp does it belong to? Does it go over here with like 8 and 16 and 25, or does it go over here with the prime numbers 2, 3, 5, 7, 11, and so on? And well, for that matter, what's the difference between a composite and a prime? Well, it turns out prime numbers have exactly 2 factors. That's it. So like, for example, the number 7, well, that is 1 times 7, and that's it. So a prime number will be the product of itself and 1, nothing else. So another example would be, well, 2. 2 is 1 times 2. Another example would be 6. 6 is 1 times 6, but it's also 2 times 3. So that doesn't get to play. Composite numbers, by comparison, they have more than 2 factors. Mathematicians are very careful with their language. When they say more than 2 factors, that means they have more than 2 factors. So a lot of the time, people say, well, look, the number 1, it can't fit here because it doesn't have more than 2 factors. 1 times what equals 1? Well, only 1 times 1, right? That's not more than 2 factors. That's just 2 factors. That's just 2. 1, 2 factors right there. So they think, well, maybe it is in fact then prime, right? But 1 is just 1. That's not 2 factors. That's 1 factor. That's just 1 factor. That's not 2 like this has 2 factors, 1 and 7. That's 2 factors. This is just 1 factor. Doesn't seem to fit very well with either. Now let's talk about the composite. Well, maybe 1 does have more than 2 factors. I mean, I can keep going on forever and ever and ever, right? 1 has a lot more than 2 factors. It has 1 and 1 and 1 and 1 and 1. In fact, that's 1, 2, 3, 4, 5, and so on. It has infinitely many factors in that respect. And I could also go over here with these prime numbers again. Well, there's 2 factors. That equals 1. Where does 1 fit? Seems to be an oddball. Man, well, let's take a look. We'll get to the bottom of this in just a minute. Let's look at the fundamental theorem of arithmetic. Well, that's a lot of fancy words right there, and I think in order for you to really understand what's happening here and how much of a big deal this is, we have to understand what this means. Fundamental, well, that means it's foundational. It means this is like super important. This is a foundation. It's like bread for a sandwich, or like a tortilla for a burrito. This is like super important. Now, theorem, it comes from the word theory. It's like idea. And arithmetic, well, that's math, but in particular, it's calculation. So the fundamental theorem of arithmetic, what that really means is like the basic idea of math. The basic idea of numbers and math and how they work together. You see why that's a big deal? That might not seem like much to you, but that's a big, big deal. Now, here's what the basic idea of numbers is. It's the fundamental theorem of arithmetic is that all natural numbers can be expressed as the product, as, a unique, I almost missed that, that's a very important word, product of prime numbers. Wow, there's a lot in there. Now, first of all, natural numbers. Natural numbers are the caveman numbers. They start with 1, 2, 3, 4, 5. They're caveman numbers, like counting numbers starting with 1. Do you see? So any natural number can be expressed. Expressed means written as. Okay? A unique means unlike any other. Product means it's like the end result of multiplication, and prime numbers have exactly 2 factors. So what the basic idea of numbers says is that all of the natural numbers, well, we can arrive at those from multiplying prime numbers together in a unique way. In fact, the word composite means like there's several things that are involved in making that. It's not just one thing. Like if you have soup, it's composite. There's lots of stuff in it that make it. It's not prime. Prime is just like one ingredient. It's like, prime is like, it's like in chemistry, it would be an element. It's like the most basic thing. It can't be broken down anymore, whereas this is put together from many pieces. So we're saying that these many piece numbers, the way we get those is from multiplying these primes together. So let's take a look at, well, an example of how that would work. Let's take a look at, well, let's do 15. Now, 15 is 3 times 5, yes? It's also 5 times 3. Now, wait a minute. We just said that in the fundamental theorem of arithmetic, you know, the most basic idea of numbers, that the expression must be unique. And these are different, right? Are they different? Well, it turns out they're not. That's called the commutative property. It says that when you change the order of multiplication, the product doesn't change. It's the same. These are actually the same. Okay? So there's one prime number, there's another prime number. That's how you get 15. You could do the same thing with 18. So 18 would be 2 times 3 times 3. You could have rearranged those any way you wanted, but that's it. There's no other prime numbers that multiply together to make 18. That's it. That's why it is unique, you see? Now, let's suppose 1 actually was prime. Well, that's different than it was before. Do you see? And it's different still. And then, like, I could keep doing that. And then this is another iteration, and it's different again. 1, turns out, is not prime. If it was prime, then all the things, like the most basic thing we know about numbers would be wrong. And, well, math is a big deal. It has major consequences. Without math working, well, all of our technology wouldn't work. Like, if math didn't work, if 1 was prime, you know what that would mean? That would mean we wouldn't have any Snapchat. Our technology wouldn't work if 1 was prime. 1's not prime, and it's also not composite. It doesn't matter how many times you list the 1, it's just itself. So, there you go. Now, if you want to see how this works, I would like you to try, well, maybe just take the number 24 and express it as the unique product of prime numbers. All right. Should we do it with you? Go ahead and pause the video. Let's try it. Try it on your own, and then we'll see. Now, 24. 24. Now, when we're talking about prime numbers, we're not going to include 1. If we just did all of the factors, now this is not answering the question. If we did all the factors, that would be 1 times, all the factors would be 1, 2, 3, 4, 6, 8, 12, and 24. That would be all of the factors. So we could do 1 times 24, and we could do 2 times 12, and 3 times 8, and 4 times 6. And the next would be 6 times 4, and those are the same because of the commutative property, do you see? Now, these are not prime arrangements. In fact, none of this list right here actually is a unique way to express this as the product of primes. This one, though, could be. All of them could be, actually. 8 is 2 times 2 times 2. Do you see? That's the prime factorization of 24. 3 times 2 times 2 times 2 is 24. Now, what if we took this one right here? Because we could start that way. Now, 2. Now, what is 12? 12 is 3 times 4, right? And 4 is, of course, 2 times 2. So this would really become 2 times 3 times 2 times 2. Same thing. Do you see? It's a unique expression. It's a unique product of primes. We could do the same thing with 4 times 6. Now, 4 is 2 times 2, right? And 6 is 2 times 3. Same thing once again. So every single number, every single natural number can be written as a product of prime numbers in a unique way. There's no other way to write this. Kind of a big idea. That's why 1 isn't prime. It's also not composite because it doesn't have 2 factors. Okay. Now, what about relative primes? I was sort of like, is that like aunts and uncles and grandmas and nieces and cousins and nephews? Yeah, no. Now look, here's some examples of numbers that are relatively prime, and these are numbers that are not relatively prime. Let's take a look at their factors, because one of the things we're doing with prime numbers, and one of the reasons we have to learn about prime numbers is, well, for factoring. There's lots of reasons to factor. Sometimes you do primes, sometimes you don't, but anyway, relative primes. Relative primes come into play when you start dealing with fractions. Let's say we want to do 3/8 plus 21/4. That seems like a silly number. But if these are relatively prime or not, it's going to change how we're going to find our common denominator. That might not seem like such a big deal. You learned how to do that in 5th grade, but what about now? A little different. That's where we're headed. So let's take a look at 3 and 8. Now, 3, 1 times 3, those are the only factors of 3. Not just talking about the prime factors, we're just talking about any factors. Whereas, well, 8 is 1, 2, 4, and 8. Those are all the factors of 8. Now 10, well, before I get ahead of myself, I'm saying these two are, yes, indeed, relatively prime. And so are these two. These two are relatively prime. 10 is 1, 2, 5, and 10. Those are the factors of 10. Now 81, it's got a lot. 1, 3, 9, 27, and of course itself, 81. These two numbers are relatively prime. What does this pair and this pair have in common? Now, and these won't have that same thing in common because these are non-examples. These are examples of relatively prime. So 2 is 1 and 2. 12, 1, 2, 3, 4, 6, and 12. 10 is, again, 1, 2, 5, and 10. 15 is 1, 3, 5, and 15. So these two don't have the same relationship. Like these two things right here do not have the same relationship as these two things right here. Do you see what it is? Do you see it? Here's what it is. Look, 3 and 8 are relatively prime because the only factor they share is 1. Same with 10 and 81. The only factor that they share is 1. That's why they're relatively prime. Relative prime numbers only share a common factor of the number 1. That's it. You see, this one has 1 and it has 2. That's why they're not relatively prime. This has 1 and it has 5. Not relatively prime. Do you see how that works? Relatively prime numbers, they share just one common factor, nothing else. Now, why we got you here, we've got to talk about other reasons to factor, because sometimes we don't want to factor and look for prime numbers, because sometimes the primes aren't actually very helpful. Sometimes we want to find perfect squares, and other times we want to find perfect cubes or fourths or fifths or all kinds of things. Now, a perfect square is a number times itself. A perfect cube would be a number times itself 3 times. And a perfect fourth would be a number times itself 1, 2, 3, you guessed it, 4 times. In other words, a perfect square is a number squared. A perfect cube is a number cubed, and a perfect fourth would be a number to the 4th. A perfect 27th would be a number to the 27th power. That seems kind of silly, right? But the perfect squares, when you're factoring and looking for a perfect square, you're looking for a number that's squared. So it turns out 4, that's a perfect square. That's 2 times 2. Do you see? Another example of a perfect square is 25. 25 is a perfect square. It is 5 squared. Do you see? 25 is a perfect square. So if you were asked to find a perfect square that's a factor of 50, well, there you have it. That's a perfect square. That's a factor of 50. Now, where that's going to come in is in the very near future. You're going to be doing things like the square root of 50 or the square root of 8. Square roots are looking for perfect squares. Do you see? And this one has a factor that's a perfect square. And so that's why it's going to make it much easier on you if you can find the perfect squares. Cubes, perfect cubes. Like, you're going to be doing a cube root of 27, which turns out to be 3 because 3 cubed is 27. So you might be asked, well, what is a perfect cube that's a factor of something like 16? Well, do you see 16 is 2 times 8? And 8 happens to be 2 times 2 times 2. That's 8. This is a perfect cube. So sometimes you're factoring, you're looking for prime numbers. Sometimes you're looking for perfect squares or perfect cubes. Sometimes you're looking for other things. You have to be flexible. Factoring is not just about breaking a number apart. That is what factoring is, but there's usually a purpose. There's a reason you're doing it. Okay. Before we finish, I have one question for you. And we're going to get to this question in the next video. Let's say x is a number. Let's say x is a natural number. We'll narrow it down, right? X is a natural number. Could it be prime? What do you know about x? What conditions need to be met in order for x to, yes, be prime? And then, well, what about x squared? Could it be prime? Does it have to be prime? Does x have to be prime? Explore this a little bit. Try it. We're going to talk about it in the next video. The whole purpose of this question right here, by the way, is to, well, make sense of all the things you've been learning about prime numbers in this video and factoring and all that kind of stuff. So anyway, I hope it's been helpful. If it has, you could really help me out. You could click like and maybe even subscribe, and you should definitely visit my website. It's thebeardedmathman.com. On that website, you're going to find all kinds of help for teachers, for students, for parents, for everybody. Anyway, it's a good place to go if you get confused. Now again, I hope that you have learned about prime numbers, and I'm sorry if I had to make you confused in the process, but unfortunately, if you're never confused, you don't learn. Anyway, until next time, thank you very much for watching. Oh, I almost forgot. If you have questions, comments, concerns, you can leave your comments down below. Anyway, thank you for watching.